Oh, okay, cool. Yeah. All right, first thing, questions on L'Hopital, because I'm ready to move into chapter 4 today. Are there any questions over L'Hopital homework, problems, anything you want me to go over? Yes? Do you have one in particular or? Right, so your question is on dropping something. Is there something in particular you don't get about it or like? Yeah. Okay, let me do one like this then. Limit. So let x go to 0 from the right. And we'll do one that I've actually, I think, done this one already. That way we don't have to hash through all the details again. So on something like this, you know what, I just realized since I don't have my camera, I don't need this mic. So on this one, real quick, we let x go to 0. This goes to 0. This goes to negative infinity. As we talked about, what natural log does is you approach 0 from the right. Yes. Okay. So the question is which one to drop down to the bottom. So let me show you both scenarios side by side. The first scenario, right, would be where I drop the x down, leave the natural log on top, and drop the x as a 1 over x. The other scenario, second choice I have, would be to leave the x on top and drop the natural log as a 1 over natural log x on the bottom. Do you see the difference between those two? Now on this one, if I let x go to 0, natural log of 0, that goes to negative infinity. And then 1 over 0 gets huge, right? So this is infinity over infinity, so I can use L'Hopital here. Here, if I let x go to 0, the top goes to 0. And the bottom is 1 over, and we already know that goes to negative infinity, right? So 1 divided by a huge number should be a really small number, right? So the bottom goes to 0. So I can use L'Hopital here as well. You see that in both cases I can use L'Hopital. Good with that? So which of these is better? Well, this one, when I do L'Hopital, the derivative of the top, derivative of natural log of x is 1 over x. And then the derivative of the bottom, I did that before last class. The derivative of this is the same as trying to take derivative of x to the negative 1, which is negative 1x to negative 2, which is negative 1 over x squared. Okay. So that would be the derivative of the bottom, negative 1 over x squared. And then we flip it. That's exactly what we did in class last time. We flipped it and then everything, we got an answer. Okay. This one, however, if I do L'Hopital, the derivative top's easy, right? It's just 1. But the bottom is a problem because how are you going to take derivative of this? You can't just take derivative of the bottom because this is a quotient. You would have to apply the quotient rule. So let me do that. I would take quotient rule says take derivative of the top times the bottom minus derivative of the bottom times the top over the bottom squared, right? So the derivative of the top would be 0 times the bottom, natural log x, minus the derivative of the bottom, which is 1 over x, times the top, which is 1, all over the bottom squared. And this isn't exactly something I want to mess with. See how this is ugly? That's better. This is just powers of x. So algebraically, I'm happier to go and manipulate this than I am to go manipulate that. Now, the only way that I would know which of these is better is by kind of seeing what I would have to do if I dropped one versus the other. Like the further ahead you know which one to do. Sometimes you actually just have to just try and see which one works out. Does that help?
Yeah.
Okay, good. Anything else? L'Hopital, yes. Well, let's take a look at it. What is it? Okay,
Right.
okay.
It's not an X over X, and I went about it today, and I just-
This over this?
Yeah.
Okay, so, all right. You sure that's the problem? Let's see, let's see what's going on here. What is happening up top? Where's it headed? Negative infinity. Where's the bottom headed? 0. Is that L'Hopital? That's not L'Hopital, right? You don't have L'Hopital there. So what is this? It's just negative infinity. Think about what's happening here. Your numerator is getting bigger, right? Bigger and negative. And you're dividing by a number that's getting smaller. What happens if, let's just say you take a number that's, let's take the number 5 and start dividing it by small numbers, 0.1. You get, what do you get there? 5 divided by 0.1. You get 50. Okay. What if I go smaller? 5 divided by 0.01 can become 500. So if I have a number on top and I start dividing by smaller and smaller numbers, the ratio gets bigger. Understand? Here, the numerator is, well, the denominator is getting smaller, right? I'm dividing by smaller and smaller numbers. And the numerator is already trying to get big. And so the denominator is almost helping it get bigger. So there's no work to be done here. There's absolutely nothing to show. You just put negative infinity and be done. That's number 9. Yeah. Yeah, always check, because you have to have infinity over infinity or 0 over 0 to use L'Hopital's rule. Other than that, we should be able to figure out the answer. Let me switch this up. What if I flip that over? What if I flip the fraction over and ask you for this limit? Limit x goes to 0 from the right of x over natural log x. Let's check again. The top heads to 0, right? And the bottom heads to negative infinity. So again, this is not L'Hopital, but we should be able to determine what that is. The top is trying to get small, and you're dividing it by bigger numbers. What happens when you divide something by a bigger and bigger number? It gets smaller and smaller and smaller, right? So again, these two are kind of helping each other out. So this would go to what? So this one goes to negative infinity. This one goes to 0. The only time you have a problem is when you have like 0 over 0 or infinity over infinity, because here you're saying I have a really, really small number divided by a really, really small number. Right? This one's trying to be small, but when you divide by a small number, it tries to become big. So they're like, these are at odds with one another. Infinity over infinity, same idea. You have a number that's getting big divided by a number that's getting big. You don't know who's getting bigger faster. You have to see like who dominates, the numerator or denominator, which one is winning the battle. Other questions or clarifications?
Zero over negative infinity equals 0.
Okay, let me see here. Okay, you have a calculator? So I'm going to try and show why 0 over infinity goes to 0. So what I'm going to do, remember, this is in a limit, right? Please don't ever think when I write this down that I'm talking about the number 0. I'm saying something that's getting closer to 0, right? Divided by something that gets bigger. This is all within the limit that we're talking, right? So if you have your calculator, let's take a number. Let's just start with the number on top. Let's start with 1, and on the bottom, let's start with 1. 1 divided by 1, we know this is 1, right? So that's 1. All right, let's let the numerator get smaller and the denominator get bigger. Okay, so on top, I'm going to go 0.1, and on the bottom, let's do 10. Do that on your calculator. Do 0.1 divided by 10. Yeah. 0.01. Okay. All right, now let's let the numerator get smaller, 0.01, and divide it by, now let the denominator get bigger. You're gonna get 0.0001. Okay, so let's do one more. 0.001 over 1,000. What do you get there? 5 zeros?
Yeah, you get 5.
Okay, what's happening to these numbers?
They're getting smaller.
They're getting smaller. Because what's happening up top? The top is headed towards 0 and the bottom is getting bigger. So this right here tries to make that number smaller, but it's already getting smaller. So it's like assisting the whole goal of getting smaller. Make sense?
Yeah.
If you flip that over, right? If I flip these over, it would be opposite. So if I flip this over and I put the 10 on top and the 0.1 on the bottom, we're gonna get 100 here. And if I do this and flip it, I'm gonna get 10,000. And then the next time over, it's gonna get bigger. So when you flip this and do infinity over 0, you get the opposite effect and it gets huge. So this is what I was mentioning last class. I think it was last class. I said that this whole idea of limits is really like a number sense. Having an idea or sense of what's happening with numbers and fractions, right? Something gets big, the other thing gets small, or the other way around, they both get small, they both get big. So we have an understanding of what's happening. Which is really what separates calculus from algebra. Is that algebra, we give you a fraction, right? And that's just a number. But in calculus, we're saying what's happening is things start to like go somewhere, to approach something. All right, let's move on. We are starting chapter 4. Chapter 4 is applications of derivatives. Now we have already talked about some applications. If you recall, the application that we've done so far is related rates. Y'all love those problems, right? You had a quiz, you did great on the quiz. So I think y'all want me to put more of those on the test. Can we do a related rates test? Just nothing but word problems? No. Yes? No. Yes. All right. Okay, let's do that. So we are going to do applications, right? More applications, but they're not going to be the related rate word problems. Until we get to the ones you're not going to like is 4.5. Those are word problems, right? But everything from 4.2 through 4.4 is basically building all the tools, getting everything in order so that we can handle these problems. This right here, optimization, is a major goal of this class, is for you to do optimization problems. I'm in my Cal 3 class, we're doing optimization right now, but we're just doing it in higher dimensions. So this is like one of the main uses, one of the most useful parts of calculus is being able to optimize something, right? So before we can do it, let's set the framework for it. So we're going to start with 4.1 called maximum and minimum values. So there are 11 notes in this section. Let's go through each one. The good thing about this is that it's very visual, so most students can handle it. And then at the end, we get a procedure, and the procedure, most students can follow it. So there's nothing crazy here. There's just a lot of things we have to get through. All right, so we're going to talk about some definitions. Don't sit here and copy these all down. You have access to these, right? So first, we're going to define what's called the absolute maximum or minimum value of a function. So if you're given a curve f, so given some function f, can y'all read this? Make it bigger. You okay? Given some function f, defined on some domain. Okay, so you have some curve drawn, and some number c in the domain. So we have graph. And then there's some number c here. We've got some graph up here, right? It says here that f of c, that means the height of that point, f of c at this point right here, is called the absolute maximum value of the function f on that domain if f of c is bigger than or equal to f of x for all x in the domain. Okay, that just means that this is the highest point on the graph. That every point around it is equal to it or below it. All right, that would be the value of the function. Where's my picture? Okay, it's coming. I'll show you the picture in a minute. Oh, you know what? Let's do it right here. I'm gonna have to make this a little bit small. Okay, look at that graph right there. Do you see an absolute highest point on that graph? Yeah. That right here, right? Right about there. That looks like the highest point on the graph. That would be considered the absolute maximum value of the function. So whatever this y value is would be the maximum, absolute maximum. Let's see, what about the absolute minimum? The absolute minimum value would be the lowest value of the function. Make sense? Absolute max, absolute min. These are also called, there's other names for these in different textbooks, and you'll hear me use it. Instead of saying absolute maximum value, I might say global maximum value. I also might say the extreme value. So these are all synonymous, right? All those terminology, all three of those different terminologies mean the same thing, right? So you have an absolute max, absolute min. Now, what's the difference between absolute maximum, absolute minimum, and local maximum and local minimum? These are two different concepts. So given a curve f defined on some domain, so again, we have some drawing of a graph, f of c and some number c in there, f of c is called the local maximum value of f on the domain if f of c is greater than or equal to f of x for all x, and here's the key word, near c. Right? If you go back up and you look at the definition for absolute maximum value, it says for all x. Okay, this says for all x near c. So the way I like to think about this is that if you have a graph that looks like this, we're going to do examples. You have a graph that does that. This point right here, the y value of that point is the absolute maximum value. There's no points higher than this one. But this point right here is called a local max. Because even though it's not the highest point on the entire graph, it's the highest point near that point. So it's like king of the hill, that hill, just that hill though, right? This one's king of this hill, but is also the king of all hills. Does that make sense? So these are two distinct ideas, all right? Absolute maximum, absolute minimum. Also, if your function is defined on a closed interval, the endpoints are always referred to as local maximums or minimums. Let's just start looking at these pictures now. Okay, this is just all the framework of the definitions. I think this all makes most sense when you look at the examples I have here. So look at this right here. That is a function that is defined starts and stops. Let's start by identifying the absolute. We already did that right here. That right there is the absolute max, right? It's the absolute max. And this point right here is the absolute minimum. Make sense? All right. Let's look for local maximums and local minimums. So let's start with local maximums. Anyone want to tell me where you see a local maximum? Go ahead.
Yeah.
Yeah, the absolute maximum is also a local maximum because it's a king of a hill, right? It's a king of, in this case, it's the king of all hills, but it is a king of some hill. So this would also be a local max. Any other local maximums? the endpoint. And this right here is a local max also. So local max. Because this is also like king of the hill, even though it's not a hill, it's at the very end of the function. So this point right here is higher than all the points near it, isn't it? All the points to the left, it's higher than those. So it's a local max. How about local minimums? Is this a local min? Yeah, it's a local min. Local, right? Local min, not local, local. Local min. Local mins. Oh, wait, hold on, I missed the local. Go back to endpoint. Were you all sitting there thinking that that's a local max? Okay, it's the highest point in that general little area. Do we have any other local minimums? Okay. So when we look at this graph, right, it has the lowest points, local, low, right? All of these points are called extreme values of the function. They're the extremes, right? You have local extremes and global extremes and then endpoint extremes. Any questions on this concept? That's the same curve, isn't it? All right, let's look at this one. So I put arrows there. The arrows imply that that function continues to go up, right? Like the function goes up on both sides. All right, yeah. Let's start with, you want to start with absolute maximum, like the highest point, the lowest point. All right, absolute maximum, what do you think? Right here? What do y'all think? Is that the global or absolute maximum value of this function? Seeing some yes, and I'm seeing some no. Who says no? Who, you want to explain? Yeah.
So.
Exactly. You can't say this is the absolute maximum because this point right here is higher than that point. To be the absolute max, you have to be the highest point on the entire graph. So there is no highest point because this arrow implies that that just keeps going up to infinity, right? It's same with over here. So in this particular case, you have no absolute maximum. No absolute max. Now, what about minimum? You have an absolute minimum. Looks like it, right? Right about here. This is an absolute minimum. Now, just so you understand, the absolute minimum is the actual, whatever this number is the absolute minimum, all right? So the absolute minimum occurs at a point, but the y value is that. The x value is where it happens. So this tells you where it happens, and then you come down and come over here, and that's the actual value. So no absolute max. What about locals? How many local maximums do I have? One. Good. It's right here, right? I'm just going to put L max. Is that all right? So I don't have to write local over and over. That's the local max. Yes. Has to be the highest point on the entire graph. Local only has to be the highest in that little neighborhood, this little area, and just in a little small region. Every absolute maximum is also a local maximum. No, for both, for both. This is also a local minimum. It's the lowest point on the entire graph, but it's also the lowest point on this little area, right? In this little area, it's the lowest. So every absolute max will also be a local max. Every absolute minimum will also be a local minimum. I have, let's see, what else? Another local min here, or a local min here. That's our first one. And then right here, same one, right? That's a local min. Is that the stack of quizzes? Yes. Who needs their quiz? The grades have been posted, but the exam don't have the grades. Not the exams, the quizzes. Right, local min, absolute min, local max. There is no absolute max. Clear? Right, this function was not defined on a closed interval, right? It was an open interval, meaning that the left, it keeps going this way, this keeps going that way, right? So we didn't have to consider any endpoints because there are not endpoints for this graph. Say again? And okay, listen to what I'm saying. The absolute minimum is going to be the lowest point on the entire graph. If I call this an absolute minimum, is that the lowest point on the entire graph, right? So you're not going to have the absolute min in two different places like that. Now you could have them. It could happen. Okay, if you had a graph that did this, I don't know, it came back over here and then like that, then do you see that this value and this value, they're the same? This would be a local, this would be they would both be locals, but then the absolute minimum would be the same because it's the same y value, right? So that the absolute minimum or maximum can occur at multiple places. In this particular case, it's not though. These aren't the same y values. Got it? Okay. Look at another graph. There you go. There you go. All right. Let's talk about what do you want to do? Absolutes first or locals? It doesn't matter. You don't have to do it in any particular order. You want to do the absolutes or locals? Absolutes. Okay. Let's start with max. Absolute maximum value. There's two different places it occurs. Do you see that? So right here, absolute max, absolute max. I'm not saying that there are two absolute maximums. I'm not saying that. There's only one absolute maximum because it's the y value. It's whatever that is, right? It's just the fact that it occurs at two different places. But I only have one maximum value. And then the min is the same thing, right? Absolute min occurs at two different places. Whatever that minimum value is the same as that minimum value. So this would be our absolute min. Only one actual minimum value. And then locals, what's this one? Local max, because it's an endpoint, right? And it's the highest point over here. This one, local min. This one, local max. It's the highest point in this little neighborhood. This one is also a local local min, right? And then here, local max. Is this pretty intuitive? Visual, yeah. The extreme value theorem. So we finally get to our first theorem. Very important theorem. I'll make it bigger so you can read it. The extreme value theorem says If f is a continuous function, continuous functions are functions you can draw without picking up your pencil. If your function is continuous on a closed interval, which means it starts at a point and ends at a point. If that's the case, then f has to attain both an absolute maximum and an absolute minimum. So if you're going to draw a function that starts at some x value of a and ends at some x value of b, and when you start it and get to whatever the endpoint is, wherever it is, that you have to connect those points with a curve, then you have to have a highest point and you have to have the lowest. Right? There's no way to avoid that. Imagine I draw that, I have to somehow get over there and got my pencil. So most point. Does the theorem make sense? Does it seem pretty logical to you that that would be the case? Yes. I'm going to give you a couple of more examples to look at here. I don't know how easy that is to see, but there's a starting point, an ending point, and I'm going to draw without picking up my pencil. I'm going to connect these two with a curve. Right, there we go. I connected those with a curve, didn't pick up my pencil. When I did that, I created an absolute minimum and an absolute max, right? And the theorem guarantees it's going to be there, right? The theorem says definitely, for sure, 100% you will have an absolute max and absolute min. Let me give you another example. There we go. I connected them without picking up my pencil. Also, it has to be a function, so it has to pass the vertical line test. You can't draw some crazy stuff, right? It has to be a function still. If I do that, then let's see what I've got here. Absolute min, max, right? No way to avoid it. Boom, straight line. Where's the absolute max? Right endpoint, absolute min, left endpoint, okay? Last one. That's an arrow that goes up forever. So this is a little arrow goes up forever. Do I have an absolute max? Thought I just said I had to have one. It's infinite. It's going to infinity here, but I thought the theorem said I had to have one. It's a closed interval. I start and end at some point. So it's closed, but what's wrong? It's not continuous. See, I just drew a function that wasn't continuous. Yes, if I draw something that's not continuous, where you have to pick up your pencil at some point, it is possible for me to draw something that doesn't have an absolute max or an absolute min. It's possible for me to do that. But see, I violated the theorem here, right? So this doesn't count. I was trying to trick you, right? So this does not count. That's why it's important. It's absolutely essential in the theorem that we have the continuity of the function. If we don't have the continuity of the function, then you can't guarantee me an absolute max and an absolute min. And then you also need the closed interval because you need to end somewhere in, at both endpoints. You need to stop. Okay, good. Now we have another theorem. This theorem, I almost don't like giving this theorem in class, but I guess it's useful, but it confuses students. So this says, if your function has a local maximum or minimum value at some point C, and the derivative exists. So let's say you have a function and you have a local max somewhere. That's a local max, isn't it? This theorem says if you have a local maximum at some value C, And the derivative exists here. Now, we have to go back and think about derivatives. Do you remember where derivatives fail to exist? There's three different ways that a derivative can't exist. A jump, or break in the graph, vertical asymptote, and cusps and corners. Very good. Those are the three places that derivatives can't exist. So this theorem says, if you're talking about a local max at some point C and the derivative exists, so here you don't have a jump, you don't have a vertical tangent, and you don't have a cusp or corner, then this theorem guarantees that the derivative at that point is zero, which means that the derivative being zero means the slope of the tangent line, right? If I draw a tangent line, I'll draw it. That's my tangent line. What's the slope of that line? Zero, which means the derivative at that point is zero, right? The derivative gives us the slope of the tangent line. So the theorem says, if you have a local max and the derivative exists at that point, then we're guaranteed that the derivative has to be zero. So you have to be careful with this theorem, because what about this? Is that a local max? Is this point right here, this top point, is that the highest point on the graph? Yes. Right. Does this theorem apply? No, because it says that if this is a local max, which it is, and the derivative exists here, does the derivative exist at that cusp? No, then you can't use the theorem. The theorem says we have to have that it's a local max and that the derivative exists, and then we can say for sure that the derivative is zero. And it works also for minimums. Look right here. Is that a local minimum? Yes. Does the derivative exist here? Yes. And then what does the theorem say the derivative has to be? Zero. So you can see it, right? It's flat there. But there's something even more profound in this theorem that I want you to understand. And this has to do more with logic than it has to do with the theorem itself. All right. How many computer science majors do I have? A couple. All right. So one of those most important things in computer science is logic. And it turns out that in mathematics, logic is one of the most important things. So when we give a theorem or a statement like this, you have the if, okay? If, and then you have some statement which we usually call P. If P, then Q, all right? So if F has a local maximum or minimum, this right here is the if P, all right? Oh, sorry, and all that is if P, okay? So if that's true, right? If that's true, then this is the result, right? That's the rule. If P, then that's a logical structure. Has anyone done logic? Anyone here taking logic class? Truth tables and all that stuff? Okay, yeah. So this has to do with that. So when we have a statement that says if P then Q, you are not allowed to change that order without proving that it's true the other way. So if you say if P then Q, you are not allowed to say if Q then P. You are not allowed to do that. You can't just switch the order and it's still true. So what I'm saying is that with this statement, we have to have these conditions, right? And then we can conclude that the derivative is zero. You are not allowed to say that if the derivative is zero, then all of those conditions are true. You can't just switch it. Let me give you a different example that I think is easier to comprehend for most people. If I live in Texas, then I live in the United States. Look at that statement. So what I mean by this is, if I'm standing physically in Texas, right? Then do you agree that I'm standing in the United States of America? Y'all agree that this is a true statement? Yeah. Okay, can I switch the order and it still be true? If I'm standing in the United States, then am I standing in Texas? Not necessarily. I could be standing in Texas, but Does this statement hold all the time? No, I could be standing in California and then not standing in Texas, right? So these implications only go in one direction. They do not go in the other direction. Those of you who, computer science again, when we have a statement that goes in both directions, where you can read it both directions, we write it differently. We do this, we write P, I, F, F, Q. P, if and only if. Q means that you can go either way. You can say if P then Q, or you can also say if Q then P. You can switch the order. So there are certain statements in our logical, there are certain statements that are if and only if statements. And then there are certain statements that are only implications in one direction. So I don't want to get too much into logic and stuff like that, but I think it's important for you to understand when I give you a theorem, you're not free to just start rearranging things however you want. You can only use the theorem in the way it's presented to you. All right. The bad thing about this theorem, and the reason I don't like to present it to the class, is that it starts with the assumption that we have a maximum or minimum. And then from that, we draw some conclusion. What we want to be able to do is actually find the maximum or minimum. This assumes you already know it's there. That's not useful to us. We actually want to go find these highest and lowest points on the graphs. Okay. I have one more thing to talk about with logic. So there's a very important part of our logical structure, just the way we are as humans, the way we think about things, the way we analyze the world around us. And in our system of thinking, we have this thing called the law of the excluded middle. And that basically means that for any statement that's given, it's either true or false. There's no third option, right? It either is or isn't. It's either correct or not correct, true or false, right? There's no third option, right? Is there? I don't know, 2023, there's a lot of gray area everywhere, right? But in our logical structure, it's either true, false. There's no middle. So it's the law of the excluded middle. So I'm going to put a statement on the board here, and I want you to tell me whether or not this statement is true, all right, or false, because there's only one or the other. All pink elephants in this room have wings. Is that statement true or false? So I'm hearing true. True. Yeah, so if you believe that this is a false statement, what do you have to do? To prove that statement's false in our logical structure, to prove this is a false statement, what would you have to do? You have to find the pink elephant in this room that doesn't have wings. And then you can prove this to be a false statement. We call statements like this vacuously true. All right? Vacuously true, which means it's true because you can't, it's falsely true. Let me give you another example. If X is a real number, this just means if X is a real number and X squared is equal to -4. So I'm giving you an if statement, right? If X is a real number, so you're not allowed to use imaginary numbers, okay? If X is a real number and when you square it, you get -4, then Robert is president of the United States. So am I the president of the United States? Like, is that a true statement? Well, if you take a real number and you square it, can you get -4? It has to be no imaginary numbers possible. Can you square a number and get a negative out? No, not unless you use I, right? The imaginary number. So this is impossible for us to do, right? So our assumption here, the assumption we're starting with is false. That's a false assumption, isn't it? That could ever happen? Anytime you start with a false assumption, your conclusion is true. It's crazy the way our logic is. If your assumption is false, your conclusion will always be true. This goes to truth tables, right? Well, if you took logic, truth tables, if you start with a false assumption, your conclusion is always true. It's just the way our structure is. If it's not this way, a lot of things change, right? That's just weird. I'm going to move on, but. Well, I don't like this theorem because I get sidetracked. So at the end of this, I'm saying, be careful with this theorem. It does not say, this theorem does not say that if the derivative of a function is 0 at some point, that we have found a max or min. It only says that if we have a max or min and the derivative exists, then the derivative is 0. Okay, yeah, this is just an example. Like, this is a visual example of Fermat's. We have a local max. The derivative exists, no corner, no cusp, no jumps, right? No vertical tangents. Here, local max and the derivative is 0. Here, local min and the derivative there is 0. That one is like the corner, right? The Fermat's theorem doesn't work here, right? We have a local max, but derivative doesn't exist, so we throw the theorem out. Here's another example which fails. Why does this one fail? I mean, is the derivative 0 here? This is a really important example. Is the derivative 0 here? Yes. Does Fermat's theorem say that if the derivative is 0, we have to be at a local max or min? No, the theorem says if you're at a local max or min and the derivative exists, then the derivative is 0. Are we is this a local max or min? No, so can't use the theorem, right? You have to, with the theorem, you have to start at a max or min, and then you can deduce something about the derivative. All right, let's back burner that idea for a moment. We have a definition. And this is a big takeaway of today is this right here. A critical number of a function, okay? A critical number, that's the thing we're defining here. A critical number of a function f is any number c in the domain of the function. So the c that we're talking about here has to be within the domain of the function. Okay, so a critical number is any number c in the domain of the function such that one of these two things is true. Either the derivative at that point is 0 or the derivative at that point doesn't exist. Let me give you a quick example. Let's say I give you the function f of x equals x squared minus 4x. What are the critical numbers of this function? Well, I want to know where's the derivative 0 and where does the derivative not exist. If I can figure out what makes that the derivative of that 0 and what makes the derivative of that not exist, then I will have found the critical numbers. So let's find them. I need to take the derivative. What's the derivative of that function? 2x minus 4. Okay. Now I'd like to know where that's 0, right? Where is that derivative 0? Well, the derivative is 0 when I set 2x minus 4 equal to 0. And then solve that equation. You get move the 4 to the other side, divide by 2. X equals 2. This is a critical number of the function. The critical number of this function. So long as this number is in the domain of the original function. So what is the domain of this function? A real numbers. There's nothing you can't plug in. This is a parabola, right? It goes like this. There's no vertical asymptotes. There's domain. You can plug any number you want into that, right? So domain of this is all real numbers. And that number, of course, is a real number. So this right here took the derivative, set it equal to 0. I also need to figure out if the derivative ever doesn't exist. So let me look at that scenario. Does the derivative ever not exist? Does not exist. Does that ever happen? What's the derivative? 2x minus 4. Is there any number you can plug in here for x that's going to cause this to go crazy? Like if you divide by 0, a square root of a negative number, something like that. Is there any problems with this function? It's a line, isn't it? This is a line. This is a linear function. Very, very well behaved, isn't it? In terms of the domain of this. Oh, does this derivative ever not exist? Does it ever not exist? No. So I only have one critical number if x equals 2. So what I'm doing here, okay, to find a critical number of the function, what I'm doing is I'm taking its derivative and then asking 2 questions. Where is that derivative 0? And where does that derivative not exist? Let me do another example. Okay, something a little harder. If f of x equals the square root of x, find the critical numbers. How do I find the critical numbers? Take the derivative, right? Set it equal to 0. See where it doesn't exist. What's the derivative of this function? We've done this before. What is it? 1 over 2 square roots of x, right? 1 over 2 square root of x. There's my derivative. And now I have to ask myself 2 questions. First question, where is this derivative equal to 0? So I need to set that equal to 0, right? Can that ever be 0? Is there any value of x you can ever plug in to make that 0? You plug 0 and you get division by 0, don't you? So that wouldn't make that 0 be undefined, right? So side note here that we're going to use the rest of this semester. If you're ever looking at a fraction, if you ever have a fraction equal to 0, a over b equals 0, the only thing you ever have to ask yourself in that case is when is the numerator equal to 0? If you ever want to know when a fraction is equal to 0, all you ever have to do is look at when is the top 0. Do y'all know why I can go to this from here? I did something algebraically to get from here to here. What did I do? Like this right here doesn't have the b on the bottom anymore. How do I get rid of it? Multiply both sides. Right? What happens if I multiply this side by b? Cancels. What if I multiply this side by b? Well, 0 times b is 0, right? Do y'all see that this is the same equation as that one, just multiplying both sides by b? The big takeaway is this. If you ever want to know when a fraction is 0, just set the top equal to 0. So see this fraction here? I want to know when that's 0, which means I really want to know when what's 0. What's a for us? Numerator, which is 1. So for this to be true, I need 1 to be equal to 0, don't I? That's what I need, but that's not ever going to happen, right? 1 is never going to be 0. So is this derivative ever 0? Yes or no? No, the derivative is never 0, right? So far, I have no critical numbers so far, because I've not been able to find a point where the derivative is 0. The second thing I have to check is where does the derivative not exist, does not exist. Okay, let's take a look at that derivative. Can you give me any values of x that would make that undefined or not exist. I know y'all are tired. We're getting towards the end of the semester, but y'all need to like get engaged. All right? Because this is gonna make or break the next few weeks for you. Zero. So we can't plug zero into that. Do you all agree? What happens if I plug zero into this? I get undefined, right? How about negative numbers? Can I plug any negative numbers into this? Square root of a negative would be undefined, wouldn't it? Yes? So it appears at the moment that I might have some critical numbers here because there's some things that make this undefined. However, go to the definition of a critical number. A critical number of a function f is a number c, what? In the what? Domain of the original function. Whatever might be causing a problem, right? Had to be a number that was in the domain of the original function. So when you look at our original function here, what can you tell me about the domain of this? What are the restrictions on x here? Can't be negative. Can't be negative. Right? It can't be negative. So the domain is all x is greater than or equal to 0, right? So any critical numbers that we find here have to satisfy this as well. So y'all said 0 doesn't work, right? 0 doesn't work. Can't plug 0 in here. Can I plug 0 into here? Yes. So 0 is a critical number. How about other numbers like negative numbers? We know that if I plug a negative in here, it's not going to work, right? We're going to get square root of a negative. That's not okay. But can you have negatives up here? No. So I don't consider any negatives down here. The only critical number I have for this function is the number 0. Because it is the number that makes the derivative not exist. And that number is in the domain of the original function. We're going to get more practice with this. I just wanted, before we move to the next thing, I wanted you to understand like the idea of a critical number in the sense that we're going to start with a function, we're going to take its derivative, we're going to figure out where it's 0, we're going to figure out where it doesn't exist, we're going to make sure these answers are in the original domain of the function. Okay, that's the idea. Now, why is it important? Why are these numbers critical? Why are they called critical numbers? Because they are critical to us being able to find maxes and mins. And the way we can use this idea of critical number is to look at a second version of the theorem we had before that's been kind of redone. And we have this Fermat's theorem, a second version of it. All right, so here it is. If f has a local maximum or minimum value at the point C, if it does, so if your graph has a local max or a local min, if it does, guaranteed that number C is a critical number. Guaranteed. And this brings us to the final note of the section and the most important note of the section. So if you've ignored me up to this point and you're thinking about Easter egg hunts already or whatever it is you're thinking about, summer vacation on the beach with pina coladas, whatever it is you're thinking about, focus on this because this is what you need to be able to do the problems in this section right here. So this is a method. Right. So I think back to like college algebra when you're learning like, the quadratic formula, we're learning a method to do something, right? This is the final summary of how we can find the absolute maximum minimum values of a function on a closed interval. All right. So if you ever have a function that starts at a point, ends at a point, and is continuous in there, how do we find those highest and lowest points? This is how we do it. Here's a method. It's short and sweet. To find the absolute maximum minimum values of a continuous function, right? We have to have the continuity on a closed interval AB. there are 3 steps. The first thing you're going to do is find the critical numbers of the function, which is what I was just demonstrating. We find the critical numbers, and then we evaluate our function f at those critical numbers. The second thing we do is we evaluate the function at the 2 endpoints of the interval. And what we're going to have is multiple answers. We're going to look at those answers. The biggest number we get out is going to be the absolute maximum, and the smallest number we get out is the absolute method. So I say we do an example. I'll run through these steps again as I do this example. So let's go with this. F of x equals x cubed minus 3x squared on the interval, let's go -1 -1 to 2. Find the absolute max and min of this. So I want us to take a step back for a moment. And I just want us to appreciate this is a polynomial function, right? X cubed minus 3x squared. It's a polynomial function, and it has a graph. And then I'm telling you to only look at that graph between -1 and 2. And I want you to tell me, without a graph, without a computer, without any other aids, I want you to tell me what the highest value and the lowest value of that function are if you're restricted to that interval with just calculus, right? So it seems if you didn't have calculus, this would be a very difficult problem. In fact, in college algebra, you're asked to graph these and you learn about, whether or not for polynomials, you learn about end behavior, if the ends look like this or that, right? And then you learn about, maybe how many x-intercepts you have and whether or not you like bounce off the x-axis or cross through the x-axis, something called the multiplicity of the polynomial at the roots, and how many turns you have. You learn all these things in college algebra. What you never learn is where the peaks and valleys are. You never actually are able to get those. Now we can find the peaks and valleys, the highest and lowest points. All right, so let's do it. So I am trying to find the absolute max and min value of is this continuous function? That's continuous because it's a polynomial. All polynomial functions are continuous. You have to go back when we talked about continuity weeks and weeks ago. I told you all polynomial functions are continuous. So this is a continuous function, and that's a closed interval, right? Continuous function, closed interval. Continuous function, closed interval. So I'm going to use the closed interval method that I just showed you. So my first step is for me to take the derivative. I'm going to find the critical numbers, right? Find critical numbers. Right, which means I need the derivative. And that derivative is very straightforward, right? What am I supposed to do with this derivative? Figure out where that is 0 and then figure out if that ever doesn't exist, right? So let's start with figuring out when it's 0. So when is the derivative 0? And then over here, I'll put where does the derivative not exist? All right, set that equal to 0. Set that equal to 0. Nice little easy. I shouldn't say that, but do GCF out of those. Pull 3x out. You're left with x minus 2. Oops, x minus 2 equals 0. Y'all agree I can do that? set each of those factors equal to 0. What are my two solutions? What are my two answers here? 0 and 2. Okay, quick check. Are these two numbers in here? Yeah, one of them is actually in the middle of these, right? And then the other one is actually one of the endpoints, isn't it? I'm going to consider both of them. One of these, let's say this was 0, and then let's say 5. Let's just say it was 0, 5. I would throw away the 5 because 5 doesn't live in here, okay? But these both live in there, so I'm good to go. Now, is the derivative ever undefined, or does the derivative ever not exist? Look at that derivative. See, look at that derivative. Is there anything you can plug in there that would cause a problem? No, it's a polynomial, right? It's a nice, this is a nice function, so it's never going to happen. So how many critical numbers do we have? So step 1 says find the critical numbers. Whatever critical numbers you have, now go plug those into the original function. So now I'm going to evaluate. I'm evaluating f at the critical numbers. This is still step 1. So I need f, and I'm going to plug in 0, and then f, I'm going to plug in 2. So unfortunately, I have to plug these two values into this. So when you plug in 0, it's easy, right? 0. Plug in 0, you get 0. When you plug in 2 to that up there, you get what? 2 cubed minus 3 times 2 squared. This is 8 minus 3 times 4. This is 8 minus 12, negative 4. Y'all with me? Yeah. I plug these critical numbers into the original function. And that's super important, right? Because next class, we're going to be doing a different method. The second method that allows you to find highest and lowest points when you don't have a closed interval. If you take the closed interval out of here, we have a different method, and we'll be plugging things into something else. You have to be clear that in this particular closed interval method, whatever critical numbers you get here, these go into the original function. See, what I know is this. I know that something important is happening at these two numbers. It might be an absolute max, might be an absolute min. I'm not sure yet, but something important is happening here. And then I also know that something important may be happening at the endpoints as well, right? The endpoint could be the highest point or the lowest point. I don't know, right? I don't know. So what I did was I checked to see what's happening at 0. When I plug in 0, I get 0. When I plug in 2, I get negative 4. That's the first step. The second step is to actually figure out what's happening at these endpoints. That's the second step. So for step 2, I'm going to evaluate f at the endpoints. That means I want f of negative 1, f of 2. So when I plug negative 1 in, I get negative 1 cubed minus 3 times negative 1 squared. This is going to be negative 1. That's negative 1. When I cube it, it's negative 1 still, right? And then negative 1 squared is positive 1 times that. That's negative 3. Gives me negative 4. And what happened at 2? What happened at 2? We already did 2 down here, didn't we? At negative 4 as well. Let me box what we have here. I know that when I plug in 0, I get 0. I know that when I plug in 2, I get negative 4, right? I know that when I plug in negative 1, I get negative 4, right? And I already know that when I plug in 2, I get negative 4. I did that down there. You can almost look at these as like points on the graph. This one right here is negative 1, negative 4. This is the point 0, 0. And this is the point 2, negative 4. And what I'm looking for is the y values. I'm looking at these and I'm comparing them. Now I'm in step 3 of this procedure. I compare these. The biggest number I see. So what is the absolute maximum value of this function? What's the absolute max on that interval? 0. That's the highest value you get. What's the absolute minimum value of this function? -4. And it happens at 2 different places, doesn't it? It actually happens at 2 different places. So if I go to Desmos, I type in x cubed minus 3x squared, and I restrict my domain between -1, comma 2, -1, sorry, less than 2. There's the graph. Look at that. That's the function domain. We can see here, this right here is an absolute maximum, right? Absolute maximum. And what's the absolute maximum value? What's the highest value there? 0. And then I have an absolute minimum occurs at 2 different places, right? But what is the absolute minimum value? -4. Using the tool of calculus to find highest and lowest points on a graph, right? Let's do one more. And I'm sticking with pretty nice functions right now. What's going to happen is in your homework, your functions are going to get worse and it's going to get harder and the algebra is going to get harder. And that's just the way it's going to be, right? So I told you in this class earlier that I just want raw derivatives, right? Everything we've done, raw derivatives. And I told you, please try and look at the solutions on the ebook to see if you can get your answers to match theirs, because you should be practicing the algebra, right? Because at some point we will have to take these derivatives and set them equal to 0 and solve them, which is going to require some algebraic manipulations. Yeah, the day has arrived for that. So the algebra is going to get messier. Okay, here we go. I'm going to pull a problem from my Cal 3. Not that doesn't make it hard. It's a little part of a problem that they had in a bigger problem. And in that, they had to figure out the absolute, they had to find the max and min of this function. F of x equals x over 1 plus x squared. And for us, let's do it on the interval. Let's go 0 to 4. So I want us to find the absolute maximum values of that function on that closed interval. Would y'all like to look at the picture first, or just let's do it? No, let's do it. I don't want to look at the picture yet. Let's see if we can do it with the calculus. All right, so the instructions are to find the absolute max and min. Is this a continuous function on this interval? Well, the only problem you would ever have with continuity is if somehow you got division by 0 here. Is it possible to get division by 0 on this? Can you ever make this denominator 0? Only if that's -1, right? But if you square a number and get -1, then I'm the president of the United States, remember? Right? So we're not using imaginary numbers here in this class. So this is okay. The domain of this is everything. There's no problem. So I can look at every number in there without any issues. Understand? Okay, so let's find the derivative, right? That's the first step. Let's take the derivative of this. And I'm going to require the quotient rule there, right? Derivative top is 1 times the bottom, minus the derivative of the bottom, which is 2x times the top, all over the bottom squared. The bottom squared. That's our derivative, right? That's the raw derivative. clean it up is set that equal to 0. And if I just leave it looking like that. So to clean it up, I'm going to distribute the 1 through here, which basically means I just have 1 plus x squared. And then over here, I have minus, and then x times x here is x squared, so minus 2x squared. Over 1 plus x squared squared. Do not square each one of those. That's not what this means, right? You would have to FOIL that out. You have to expand it. So I'm just going to leave it as is. One more thing I can do. You'll see it on top. 1 minus x squared over 1 plus x squared squared. That is a pretty clean looking version of the derivative, isn't it? All right, now what I need to do is figure out when that's 0. Finding the critical numbers now. So where does that derivative equal 0? That's the question. So I set that equal to 0, right? I have to set that equal to 0. Yes, that's the life I have right now. It's my reality. Okay, setting that equal to 0. Hey, y'all see that? Equal 0? What did I tell you? Wrote it in red. Means that what? All I have to do is look at when the top of this is 0. This, I just look at when is 1 minus x squared equals 0. And there's 2 different ways you can do this one. You can put the x squared to the other side and then like add x squared and then take the square root on both sides. That's one way. Or you could also look at that as a difference of squares. I kind of like the idea of doing difference of squares because it shows you know that factors. That does factor, right? And then you set each of those equal to 0. And this one you get x is -1. And here you get x is 1. These are just little linear equations. So you just move things around, get x by themselves, and you get this. Get 2 answers, right? Questions on that? So far, trick question. So far, how many critical numbers do I have? 1. Why just 1? Because -1 is not in here. So I'm throwing this one away. +1 is in there. So I'm going to look at that one, but I'm not going to be looking at negative. I have to check whether or not these critical numbers are in that domain or not. What else do I need to look at? Where the derivative doesn't exist. All right, so I'm going to just do it right here. So I'm still in step 1 here. So step 1, where does the derivative not exist? So here's my derivative. I had it boxed up there all nice and pretty. The only thing that would cause a problem here is if I had division by 0 again, right? If somehow I'm dividing by 0 here, I'm going to have a problem. But can you ever make this 0? No, for the same argument from before. The only way to make this 0 is if this right here is a -1, but there's nothing you can ever do to square something and get -1. So I don't have to worry about that. I did need to look at it, but after analyzing it, I know that that's never going to be division by 0. All right, so now finishing off step 1, what I need to do is I need to take the only critical number I had, which was 1, and I need to take that and plug it into the original function. And when I plug 1 in there, what do I get? Let's see, 1 over 1 plus 1 squared. This can be 1 over 2. Yeah, it's a half, isn't it? 1/2. That's step 1. Yes. The original function. Yep, the original function. For the closed interval method, you're always plugging your critical original function. Yes. Pardon? Plugging the critical number into this. Yeah. Hey, what would happen if you plug this critical number into the derivative? What would you get? How did we get it? What did we do to get this? We set the derivative equal to 0. So if you plug this into the derivative, what are you going to get? 0. I'm just telling you, that's what you get. That's not what you're supposed to do, but you should expect to get 0 because that's where that number came from by setting the derivative equal to 0. What we want to know is what is the original function doing there? We know the derivative there is 0, but we want to see what the original function is doing at that point. All right, step 2 is I take the original function and I evaluate it at the 2 different endpoints that I was given. So at 0 and at 4. What happens if you plug 0 into that? Don't you get just 0? Right? And now plug in 4 into that. Here's the value of my function at the 2 endpoints. Here's the value of my function at that critical number. What is the absolute maximum value of this function on that interval? Which of these 2 numbers is bigger? This is bigger than this, right? This is bigger than this. You could check it with a decimal if you weren't sure, like, do it on a calculator. But this right here is the absolute max. And then the absolute minimum is 0. So if I graph this function and I restrict it to the interval 0, 4, I should expect to see the highest value is 1/2 and the lowest value is 0. And I should be able to see where those occur. So let's do it. Go from 0 to 4. And we're going to do x over 1 plus x squared. See the graph? Here's the left endpoint. Here's my critical number up here. And then here's this, right? See, we found those points, didn't we? Calculus, we found those points. Now, I will be the first one to admit that you could solve this problem in a few seconds on a computer, right? Not only could you solve it with a computer, but nowadays, if you go here, if you click on the function in Desmos, it automatically generates these points. You'll see that if I just hover my mouse over that point, it will give me the actual coordinates of that maximum, right? 1 and then 0.5. So why not just do this, right? Like, why go through all the calculus if we have the ability to just graph it and find maxes and mins, right? Remember, like, things like this were not available. Desmos has only been available in the past decade. You have to buy software to do it. Technology is evolving to the point where we can do a lot of calculus with just looking at the picture, just looking at the graphs easily, just analyzing very quickly like this. And in the real world, you would probably, an engineer or something would definitely turn to the computer to do this. I would rather have a computer go find maxes and mins than have some engineer taking derivatives like in, sitting at some desk doing it by hand, because there's more likely a chance that they're going to make a mistake, right? The computer's probably not going to make the mistake. So at what point do we stop doing the theoretical math, right, and actually just do the applied? Isn't that a fair question? All right, I think it is. You still had to have somebody write the code to make this happen though, right? I mean, like, somebody had to generate the code that creates the function and finds the maxes and stuff like that. So you have to have somebody who understands the math, right? or else at some point you lose that and then you're not able to continue programming because nobody knows the math anymore. You have to keep that foundation in there, right? And so remember that this is not an engineering class, not a computer science class. This is a math class. So I like to look at it like, yes, we could do this, but we still have to stay grounded in the pure part of what math is, which is the theory. So one more thing on that, since there are a few computer science majors in here. When I was in school as an undergraduate student, I took a class called number theory. And number theory is no, sorry, that's a different class, numerical analysis. And it was Dr. Richardson, and in our project for the semester was that we had to go and we had to find 3 different software platforms that were used by engineers, computer scientists, physicists, just 3 commonly used software platforms. And we had to basically take this software, which we call the black box. We had to feed into this software a problem, right? And then have this program spit out our answer. And our task for the project was to create a problem that we could solve theoretically by hand. Like we could get the solution and prove watertight proof of what the solution is. But then we would look at the code of the black box, the way it was programmed to solve the problem, and we would find a weakness in the code and we would exploit it. And we would have it give us an answer that was false. So that we could show the theoretical true answer and we could show that this black box gave us something wrong. Does that make sense to you? So the idea of that is that when you get an engineer or somebody building a plane or a building or something like that, right? And they're putting things into a computer and you're trusting those answers, right? Like people's lives depend on those answers being correct, or the plane falls out of the sky or something like that, right? Somebody has to understand the black box. You can't just trust the black box always, right? Someone's got to check it. Someone's got to make sure that the weaknesses are not, or at least known, right? So that the person sending the problem and says, hey, look, this particular problem, I can't use that black box. I've got to use a different black box because that particular black box is not good at these types of problems. Because of the way it's coded and written, I don't want to use that. Does it? Yeah. So, I mean, that's why we have to stay in the, I guess, pure aspect. All right. Given all that and the fact that I only have a few more minutes, you have what you need to do your homework in terms of the problems in the homework. We're not going anywhere. Hold on. The problems in the homework are find the critical numbers. First part of the second, find critical numbers. That's it. Just find critical numbers. And then the second part of the homework is, okay, now go find absolute max min on closed intervals. So the first part is just practicing taking the derivative, setting it equal to 0, figuring out where it doesn't exist. That's all you have to do. And then the second part, you have to do the whole 3 steps, sorry, that I just did. So I'd like to show you a problem, all right, that we're going to hopefully solve in the next 12 minutes. And it's an application problem. In the past, I've offered this as a bonus. Yes. Yep.
On the last part, I was able to understand 1 to 10, but I don't know. Was it supposed to be higher 3 something?
I think we can do everything in that 37 now because we covered all the different cases. Yeah. Yeah, do them and then we'll come back, and if you have more questions over L'Hopital, we can talk about that. What? So we see a lot of this on the side of the road these days, where they've got those machines, they're digging, they're burrowing tunnels or holes underneath the ground, and they're laying that big orange stuff that's fiber optic cable. Most of the time, that's what you're seeing. And so let's act like we are a company that actually installs fiber optic cable. Okay, that's what our company does. And some business asks us to present them a bid, right? They're going to get multiple companies that come with bids. And what they want to do is they want to connect two of their buildings with fiber optic cable. Now, the buildings are separated by 500 feet of water and they're 2,000 feet apart. So you have building A and building B. They need to connect those with fiber optic cable. And there's a river that goes between them that's 500 feet wide. Okay, if you don't like the river, just imagine it's a road. Okay, this could be any scenario. I'm just trying to make it make sense. So we need to go, it's 2,000 feet down and 500 feet over. We want to connect those with fiber optic. Understand the problem? Yes, but there's a catch to it. There's something we need to consider. Our company knows that it's going to cost us about $470 per linear foot, $470. If we want to install the cable below the ground, all right? And $710 if we want to go under the water, like if we ever have to burrow deep enough to go underwater, all right? So if we're just going to go, on dry ground along the side of the river, it's $470. So it's $470 for every foot we go this way. And then it's $710 if we ever have to go across the water. So the cost is different, right? Does that make sense that would be in the real world something your cost would vary depending on what you're having to traverse through, right? So the question is, you got your people sitting there, your engineers, your company people, right? The people you've hired, and you say, okay, put together a bid that we can present so we can win this bid and get the job and work it, right? And make money. How do you design this bid so as to first be competitive, but the other thing is to actually do it and make some money, right? You want to make a profit, right? So any ideas, just initial thoughts on this? Raise your hand. I don't want to just blurt out. Can you hold it for just a second? Not because you always answer, which is great. I want to
Give everybody else a chance.
exactly. I want to give everyone a chance to answer. You got something? Go ahead. So obvious one would be go straight across, okay? Or all the way up and all the way over. Those seem like two reasonable scenarios. Let's talk about the pros and cons of each. So let's go, if I go this way and across, what's a pro of that one? Not less money, I mean, less. So if I go across, it's all underwater, which is the most expensive way, right? It's all underwater, but it's the shortest distance, right? So from here directly over, shortest distance, but you're using the most expensive method, right? Here up and over is the longest distance you could possibly go, right? Well, you could go past it, but then you're getting fired, right? Like, sir, we're going to go down 3,000 feet and come back. No, okay. No, the longest distance that makes sense is to go up and over, right? So the drawback is it's the longest distance. The pro of it is that this is the way that keeps you going under the water the least, right? You have to go a bunch on dry ground, but then you have the least amount underwater. Those are the two obvious ones. Any others? Any other ideas here? Yeah. So maybe there's some variation where I don't go directly diagonally, but I go more like maybe here and then. Okay, I'm going to do that, but reverse. it would be the same as going like up a little bit and then over, right? Or like up here and then over, right? I could do that as well. Do you know which is the best way to do it? Do you think the cost is the same no matter how we do it? Raise your hand. How many of you think no matter how we do it, it's the same cost? Anyone? Okay, how many, raise your hand. How many of you think it differs? The path we choose will change the price. Okay, so we can all agree on that. So the question is, what's the best path then, right? What is the optimum path to reduce your cost to the smallest, right? What did I just say? To reduce your cost, to minimize your cost, to get your lowest point on a cost function, right? Imagine we had the cost function graphed. We want the lowest point, don't we? That's the idea. So the question is, in 4 minutes, can we come up with a cost function? Can we? So the extremes go straight across. The other extreme is all the way down and all the way over. And then there's every possible scenario in between. We can go down some amount, stop, I don't know where, and then go straight across, right? That would be the generic scenario, right? That's like the generic. So I'm going to call the distance from here to here that I don't know. I'm going to call it X. That makes perfect sense, right? If that's X, then I need to figure out what I'll call this Y. That's the distance from here to here. Let's talk about cost. Okay, how much am I going to pay to go this way? So X is feet, right? How many feet you have? How much am I going to pay per foot to go this way? Yeah, then I took it off here. It was 470 dry, and it was 710 for wet, right? To go underwater. Okay, so how much will it cost me to go this far? 470 times that distance, right? Whatever that distance is, times $470 per foot. So 470x plus, now I've got to go from here to here. How much is that going to cost me? 710 times y. Good. That is a cost function. But the problem is, or I should call it a cost equation. The problem is it has two different variables in here, right? Wouldn't it be great if this was just one variable over here, like X, and then I could graph it and I could find the lowest point, couldn't I? So if I could get everything in terms of X right now, I'd be in business. Here's how I'm going to do it because I'm really getting rushed for time here. You all see this right triangle? Yes. What's this side? 500, that's the river. Okay, what's this side? Careful.
2,000.
The whole way is 2,000. And then you have to take this away, how much we went up, right? So this is 2,000. 2,000 take away X, right? Whatever 2,000 is the whole way, and then take away the amount that we went up here. Right? Can you tell me what Y is? Staggering. This squared plus this squared equals that squared, right? 500 squared plus 2,000 minus X squared equals Y squared. So can you tell me what Y is? Square root on both sides, right? Both sides of this. Any questions? It's just Pythagorean off of this, right? So this is 470x plus 710 times y, but y is the square root of this. 500 squared plus 2,000 minus x squared. There it is. This is a function that gives me the cost. All I have to provide you is x, right? If I give you x, this spits out the cost. So I'm going to type that into Desmos, and we're going to go look at the graph and find the lowest point, and we will have optimized. And then I'm going to get a raise, and my boss is going to be happy. All right, so I'm going to do 470x plus 710 times the square root of 500 squared plus 2,000 minus x squared. I think that's it. Okay, I need to find the function. It's somewhere on here. Hard for me to find it. Let me zoom. There it is. Okay, so. Oh. I know I'm out of time, but. There we go. Do we have a restriction on X? What's the smallest X could be? 0, and then you're just going straight across, right? And then what's the biggest X can be? 2000. So if I restrict this between 0 less than equal X less than equal to 2000, there's the graph. I appreciate y'all staying. There's the graph. What's the most expensive way to do it? Top left, which is X is 0, which means going straight across. And it's going to cost you, if you do it, that's going to cost you $1,463,702. If you go the other way, which was the other extreme, that means go all the way up and straight across, it's going to cost you $1,295,000, which is better than going all underwater. But what's the best way? The best way, that one. What you do is you go 1,558 feet down and then cut across to the other building. Do it that way, you're only going to spend $1.2 million. 1.2. That's tens of thousands of dollars you've saved, right? This is the way real world optimization works. Does that make it work, like seem valuable to you at all? And imagine you're laying cable for the whole, like going through the whole city you're optimizing, you want to optimize everything, right? Because in the end, it adds up to be millions and millions of dollars perhaps. Okay, thanks for staying. I hate keeping y'all after, but y'all have a good one. The homework, finish the L'Hopital and start the 4.1. See how you do with the critical numbers. Have a good day, everyone.